what do we do to take an algebraic expression and turn it into something we can solve? We need to begin by understanding some common terms. The first major piece of this is anytime we have a variable or a number or a thing we're working on, we call that an expression. For example, 5x plus 3y is an expression. Of that expression, there are a couple smaller pieces of it that we sometimes want to indicate. For example, the numbers in front are called coefficients. Coefficients just mean the thing that tells me how many of those I have. But for example, the variables x and y, I have 5 x's and I have 3 y's. Think of x maybe as being money and y as being fruit. I would say I have 5 money, maybe $5, and I have 3 fruit, maybe bananas. So this would tell me how many of each. Remember, if it doesn't have a number in front, that's okay. That just means there's one of those things. So if I have y, maybe that's a banana, that tells me 1 banana. The 1 in front is by default. Anytime a variable gets used, it represents the same thing. So again, if I was talking about x being money, for example, then I have $2 plus $3 plus $1. So 6 total dollars. I can actually add all of these up to get one value, 6 in this case, times x. If they're not the same variable, we just can't do that. So D and A and B are not the same variable. I don't know what they are. Again, this could be apples, bananas, and pears. We can't just add them all together. They are distinct. They are separate. Now, this is a nice foundation. It reminds us of coefficients, reminds us how we can combine variables. But a lot of the problems on the GED require us to dive in and take words and convert those words into something with math language that we can actually solve. In theory, some of the real-world concepts you could probably solve in your head without rewriting them in math language. But the math language helps us double-check and make sure we didn't miss something. So let's go through each of these piece by piece to take a look at how we would interpret them. First row. Product of 5 means multiply by 5. And a number, we can just put in x, let's say. X is my favorite number to put in. If I'm going to put a variable to a number, I'll just put in x's or y's. But you could use n for number. That's fine as well, as long as you remember what your variable is. And I hesitate to use something like O for a variable, because O looks a lot like a 0 when I write it down pretty quickly. The same thing with S for a variable. My S's look a lot like my 5's, so I don't want to be going too quickly and think that I miscounted something by accident. So X's, Y's, or maybe N for number. Next row, a number decreased by. Decreased by means subtraction, so I'm subtracting 12 from the number. So decreased by is minus 12. Next row, sum of 3, that's plus 3, and the square of a number. Now watch out. Whenever we're down between two things and we think, I've got to add 3 and I also have to square something, we want to be sure we're doing the right order of operations. Order of operations that we will use for the test is PEMDAS. PEMDAS stands for parentheses, exponents, multiplication, division, addition, subtraction. PEMDAS. That's the order we have to do things. So in this row, the sum of 3 and the square of a number, what we want to do first, given two options, is the one that's earlier in that order. Parentheses, exponent, exponent. A number squared, that's an exponent thing. That's why we put the x squared first, and then we add 3 to it, as opposed to doing all of x plus 3 and then all of it squared. We don't do addition before exponents. So if we're given the choice, like in this row, that's the one we do first. And that actually applies to the next row. 6 less than the quotient of a number and 2. Now I've got two options. I could do my 6 less, or I could do my quotient. Which one comes first? Well, parentheses, exponents, multiplication, division. Division comes before addition or subtraction. That's why we write this as x divided by 2. Quotient comes first. Minus 6. That's later in the order of operations. So we'll add that on to the quotient we've already done. Or in this case, subtract that. from the quotient we've already done. Next row, 1/2 of a number. All right, that's division. Great, we like that. That comes pretty early. So x divided by 2, or 1/2 of x, increased by 15. Again, addition is later in order of operations, so plus 15. Great. Now let's look at this next row. We're getting a little bit more complicated. 4 times the result of subtracting a number from -3. Ooh, now multiplication would normally come first in order of operations, but now they've said 4 times the result, essentially telling you there's parentheses in here, and parentheses always win the battle for order of operations. So a number subtracted from -3, so -3 minus number, all in parentheses, and then that result is times 4. That's how we get the stuff on the right-hand side. Last row, the square root of the sum. Ooh, this is like a parentheses. Normally, square root would be done early. That's an exponent, essentially. But it says of the sum of a number and 3. That's sort of like saying the result of adding a number and 3. Again, basically telling you you have parentheses around this next piece, then do the exponent to that whole thing. That's why it ends up being the square root of all x plus 3 instead of just the square root of x and then adding 3 on the end. I know this takes a lot of practice at first, but we can really start to use it on some GED problems that don't even necessarily require you to solve all the way to the end. They just require you to set up the problem. Let's take a look at one. As usual, we really recommend for your best practice, pause, take 30 seconds, take a minute, at least get started on this problem. If you can get to the answer, amazing. If not, at least get started and work on it just to make sure you have that chance to really explore the problem and see what you would feel like on test day doing this question before we walk through it together. Pause, and then we'll review in a second. All right, I hope you gave that a try. Let's dive in and take a look at question number 1. First of all, I'm interested in assigning a variable somewhere, or if they have already done it, making sure that I use the right variable. So in this case, they've already told us the answer to the number of tickets. It's T tickets. It's probably the variable I would have used anyway. I like to use a variable letter that matches up with the actual name of the thing. So if I was trying to do a variable for number of baseballs, I'd probably use a B. If it was the number of leagues, I might use a capital L, or in this case, tickets, use T. Next, I'm looking for something in this problem that gives me a mathematical value. I have 1,500, I have 2,000, I have 0.5. I want to know how many are going to give me that 0.5 or that 50 cent bonus. And it tells me that it's each ticket over 2,000. Now, often when I'm doing a word problem and converting it to math, I try and go piece by piece, literally highlight or underline the whole block of text that I'm going to make into a number. So in this case, each ticket over 2,000. So it has to be bigger than 2,000 tickets. So I can take my number of tickets, subtract out the 2,000 that don't get a bonus, and anything more than that will get a bonus. So total tickets minus 2,000 is the ones remaining that will get that bonus. So this thing, T minus 2,000, has to be multiplied by the 50 cent bonus. Well, there's only one answer that has T minus 2,000 multiplied by 50 cents. Answer choice C. Now, we didn't actually even do the whole expression. We could have put in here 1,500 plus, that's answer choice C's entire expression, but sometimes just working on a small piece actually helps you go pretty fast to the answers. For example, answer choice A doesn't have the 2,000 number written at all. And answer choice D, everything is multiplied together, not added. So it couldn't have been answer choice D. Between B and C, we would have to be careful, make sure we didn't do T minus 2,000 or 2,000 minus T and mix match those by accident. But even by just taking a small piece of this, knowing that 2,000 had to be in there added to something or subtracted from something, actually got us down to B versus C right away. Now, from here, we could distribute the 0.5 across and actually simplify this into an even smaller expression. Whenever we have that opportunity to simplify down a problem, we usually do simplify, unless it's a problem like the last one where we're only setting it up. We're not actually trying to solve. In the vast majority of cases, we do simplify at some point, and when we're simplifying, the thing that most often combines is the variable. So x's or t's in that case, or y's or whatever it is. For example, in this expression, 5x plus 2y minus 7z plus 4x. Whew, okay, a bunch of variables. We don't have to worry about solving. Let's just simplify. There are two different terms that have x in them. All right, let's combine them. 5x plus 4x is 9 total x. So my expression, even though it didn't simplify a lot, ended up being 9x plus 2y minus 7z. It's a little bit simpler, and that's the form we'd expect to see in the answer choices in the end. Let's try it out on a problem where we don't actually have to simplify per se. We have to substitute and combine to get to an answer, almost really solving. Take a minute, skim through question 2, plug in, and then check your work right after this pause. Okay, let's look at number 2. What is the value of an expression when we're plugging in numbers? Now, this is not something where we had to simplify x's and y's, but we do have to plug in carefully, especially if there are negatives or exponents that might change things. In this case, we're plugging x in and getting a 3 value, and we're plugging y in and getting a negative 6 value. So the 3 times 36 and negative 6 squared times 8 is being subtracted. Watch out, when we square a negative, and it's in parentheses like we have here, squaring that negative makes it a positive. Yes, we're still going to subtract it in the next step, but squaring it by itself makes that a positive 36. So 3 times 36 and then negative 8 times 36 does give us 108 minus 288. Subtracting that out gives negative 180, which is answer choice C, as in champions. Nice work. Now, it's easy to make a mistake on this problem and actually get a bigger number by accident, multiplying that negative out, forgetting that it cancels when you square, or maybe doing something like subtracting out or only doing the second piece and getting negative 288, answer choice D. Often wrong answer choices on the GED are what we'll call classic miscalculation errors, where you added instead of subtracted, or multiplied when it was supposed to be divided. That's easy to get caught in if you're going very quickly, but the more we practice, the more you'll be able to fine-tune where you might make a mistake with a sign or a distribution, let's say, and be aware of it next time. Speaking of, distribution is one of the simplest places, maybe, to make a mistake like this. Whenever we're distributing, the most common mistake, and the reason I call it simple, is actually multiplying the first number only and forgetting about the second. Remember, when we distribute, if there are two numbers inside the parentheses, we distribute across both. So 3 times x definitely is the first part. That gives us 3x. But then 3 times 7 is the second piece, which gives us 21. 3x plus 21 is the entire distributed step. Then we could do whatever else the problem requires, maybe solving, maybe simplifying, something else. Let's do another example. 2a minus 3b inside, and we're multiplying the whole thing by 10. Well, the 10 multiplies by the first, and the 10 multiplies by the second. That gives us 20a minus 30b. Now, this might not be a mistake that you often make, but it's something that is a very common mistake to watch out for, especially as we get maybe 2 or 3 distributions in a problem and then have to simplify after. Maybe a lot like this problem. All right, take a minute and try number 3, and then we'll review the explanation. For number 3, they want the simplified form, and honestly, they didn't have to tell us we want the simplified form. We know that they're often looking for the simplified form in any given problem on the exam. Well, we have to be diligent. 4 times each of these terms So 4 times 2 is 8, and 4 times 5 is 20, so 8x minus 20. That's my first piece. Now, set that aside, go back to the next one. 2 times each of these on the inside. That gives us 6x plus 2y. At this point, I can see that I have x's in both parts of the expression. Let's combine those together into one. Adding the x's gives 14x plus 2y minus 20. That's answer choice D. Done! I will remind you that as you're going through and solving problems like this, you might actually be able to be done a little bit earlier, or at least get rid of a couple rubbish answers along the way. For example, I see that there was an 8x and a 6x. They were both positives. They're both going to add. There's no way I'm going to end up with 2x like A and B have. I can get rid of A and B right away as soon as I see that both sets of x's are positive. Again, this is a sort of thing that if you're sitting there going step by step by step and getting to the final answer is not really going to be super helpful, but on a problem that is very complicated or a lot of steps, or you're really crunched for time, noticing something like this and getting rid of half of your answers right away can actually save you a lot of steps, a lot of time, and maybe even get you to the right answer faster than somebody else who's going through every single step in the process.